listening to Future in Steel, a podcast series about the composite revolution. Brought to you by Tree Composites, winner of the 2025 Chamber of Commerce Innovation Award. Hear how challenges, vision and real-world innovation meet. How leading Dutch companies, innovators and key stakeholders share their vision on the future of industry, steel and manufacturing, strengthening Europe's position as a global economic power in a rapidly shifting geopolitical landscape. Glad you're listening. Europe's ambition to remain a global industrial powerhouse increasingly depends on its ability to rethink materials, structures and design philosophies. In offshore wind especially, fatigue has long been the invisible limiter, driving heavier structures, higher costs and conservative engineering choices. In this episode of Future in Steel, we explore how that paradigm is changing. Here are guests: Marc Vanderschueren, business developer at OCAS NV, one of Europe's leading steel and metals research institutes, and Marko Pavlovic, associate professor at the TU Delft and co-founder of Tree Composites. Hear how they talk to Maxim Segeren, CEO of Tree Composites and the regular host of the Future in Steel. Together, they examine the intersection of steel, composites and large-scale testing, from full-scale fatigue testing to breakthrough composite joints that outperform welded connections by orders of magnitude. This conversation goes deep into why OCAS exists, how testing capabilities are evolved over the past decades, and why composite joints may represent a fundamental leap forward for offshore wind, floating structures, and beyond. Marco, on behalf of Maxim, a great welcome to Future in Steel. How great you are here. Wonderful.
Thank you.
Thank you.
Wonderful.
Yeah, so thank you, Mark, also for taking also the effort of being here. I really appreciate it. I also thought it would be good to start off just on a little bit of introduction on what does OCAS and a bit on what they actually do and why they exist.
Thank you, Maxime, for granting me this opportunity to explain that, because it's not so easy indeed. OCAS stands for Research Center for the Application of Steel, and is basically a market-oriented research center for steel and the applications around that. We exist since 1991, and we were seen as basically bridging the gap between fundamental research and the industry. So really it's about industry-driven research, applied research, and also bringing that through services to the market. And since that we have been doing now a very long time, and we have to adapt all over the time, basically, from doing it only for the steel world, because that's where we basically come from, to also to the energy markets or to other markets, basically, where people need to have more information about the material or about the joint material into the application, and where they want to push that to the limit. And that's where we have been playing our role.
Yeah. Yeah, really interesting, because it is also, as you said, it is already more than 30 years ago that it was established. And if you were you already there, let's say 30 years ago, or
no? I'm in the company for 18 years now.
18 years. And do you remember the first project that you ever did, and why you got so excited to start working at?
Well, I could start from a blank sheet, and because they asked me, say, look, we've got all the research activities and big of the research activities. Wherefore our main shareholder, of course, which is ArcelorMittal, a really steel giant, but we also had to develop the side of basically the third parties, and so I could start really from a blank sheet.
Okay.
And so we started first with doing sales, but then you say no, there is much more than just sales. It's about bringing the research center to the next level.
Okay.
So, and that's why you start doing business development and trying to intersect with the researchers to bring also some new aspects into the company, and also try to help outside companies in getting better. And I think it's the interaction which has been quite successful.
Because now, in the last, let's say, 18 years, larger companies have been testing at OCAS, if I understand correctly, right?
Yes, indeed.
And can you share a bit on what those companies are and what they mainly were interested in?
Well, what we in the offshore world, at least, are quite known for is the very large fatigue testing. We had been doing qualifications for steel in towers, welded steel for the towers. And there we had basically seeing that, depending on the type of welding procedure, you could get a different type of fatigue performance. There we were basically saying, look, can we not optimize this fatigue performance? Can we not get better? Because fatigue is a real design driver for offshore structures. And that's how it basically started. And we had our own concept on fatigue-proof welding. But then you go to say, okay, if you want to do better, it has to be accepted. And you all know that. And so the certification bodies have to accept that. And then you basically say, okay, what do I need to get accepted? Well, you need a very strong mechanical loading. You need mechanical loading. So not just stimulating real test. Okay, that's not a problem. We can do that. We've got different small-scale machines and so on. I said, yeah, but if you do it small scale, I have to be on a very safe side. I have to do all these reduction factors. If you really want us to accept the results of such a test, you have to do it full scale. I said, okay, right, full scale. And that's already getting a bit more tough, if you're testing 10-ton things and so on. And then you say, okay, how much do I need? And then, it gets a bit more fuzzy, and you see that you have a big number of these things to be tested to have statistical evidence. Relevance, basically. And there we had to think strongly, so how could we bring benefit of increased fatigue performance to actually the market? And that's where we developed our own testing methodology and machinery. And this has been picked up definitely by the UK market and the Carbon Trust Offshore Wind Accelerator with all their members. And so we set up a very big project, basically to look at more fatigue improvements of robot welded joints versus classical joints, and all the standards which were established in the years 70s and 80s. And then in the meantime, we've done other projects on single-sided joints. We've been looking at beams in constructions and so on. And you see that you can get data very fast. And that's what people are looking at. They wanted it in their real application, and they want the data, but they don't want to wait years to get those data. And that's where we have been trying to basically give an answer to that. And so far, it looks we have been succeeding, but it's going to evolve further, of course.
You have new ideas.
Definitely.
If I may ask, Marc, so you have a very specific technology in your laboratory for testing the type of testing that you do and the type how you apply this loading, these millions of cycles is different to what other laboratories are doing. Can you tell a little bit more about it? What is so specific that allows you to do so many cycles in a relatively short period?
Yes, actually we're using a methodology which is called resonant bending. Mm-hmm. Now, resonant bending has been used into the past. Think about all these pipelines which were single-sided welded, so the girth weld, and there were mechanisms that existed basically all to test it all around to look for the weakest spot on the weld. Now this was oil and gas basically. So we've taken this technology, but we have modified this technology to basically first of all upscale it, and also to apply that to geometries which were just not a round pipe, but then also to a jacket node. And so that was really the difference. Yeah.
You've put it to the next level. Can you tell in simple words to our listeners, what does resonance-based bending test do compared to classical hydraulic load application?
Yeah, it's like just playing the guitar. When you're touching your string, and you see that the string is vibrating, well, that is, you've brought it into resonance. Mm-hmm. Every object has got its own resonance frequency, and we bring it as much as to close. We excite basically the whole structure of the whole component close to its resonance frequency. Mm-hmm. There it starts vibrating, and that applies the whole fatigue loading. So there is a whole lot of calculations being involved. It's not that easy. but we've made it to work.
And I think we are talking about order of magnitude of difference in frequencies you can achieve compared to hydraulic loading in such big structures.
Indeed, Marco. Typically, hydraulic frequencies, and you know that as well, huh? It's about half a hertz or to 1 hertz maximum, definitely for such a big structures.
Mm-hmm.
We are typically operating between 20 and 40 hertz,
Wow.
which is it's much faster, so you can get much more data in a shorter period of time, and that's what the people are looking at because we're talking about millions of cycles.
Mm. Thank you.
No, I think it would also be interesting. So they are looking for data, and why, right? Because we do a lot of fatigue tests, but maybe it's not clear to the listeners. Okay, what does it mean if you have a fatigue improvement? What is your experience that they actually? So they do, let's say, welding improvements for a reason. And what's your vision on why they actually are looking at that?
Well, the reason is, first of all, it's a design driver. And
what does that mean?
And it means really, it directly implies how the design is made and also the cost of the whole component, and not only the component, the whole structure. We've got different categories, so it means you have to certain thicknesses of steel, and it all depends. So it adds directly to the full cost of your component and your structure. And you know, these structures, they're getting much bigger. They're getting into deeper waters. The turbines that come out of it, on top of it, they're getting bigger and bigger. They apply much more fatigue loading. So all these structures, they have only been growing exponentially, and everybody is still using the same methods of the year 70s and 80s, and we know where that is going. The supply chain gets very difficult for the supply chain. Only a couple of people can supply really the thickness of steel and can still make these very big things. They're getting very heavy to lift. So crane capacity becomes a bottleneck. So if we can make those lighter, if we can make more compact, if we can extend the life much more easier at the end, it's these all economic factors. And you know that in the beginning, when I started, offshore wind was very heavily subsidized. Subsidies are going down very, very rapidly. There are already some farms which are operating without subsidies, but even when a bit of subsidies is needed, it's not going to last forever. So it's all a matter about fatigue. How can we ensure that we can bring more value to that market, and how can we make this market grow? And it's about energy security. Today, if we talk about offshore wind, it's also about getting a greener environment, so which is good for the planet. So fatigue has got an impact on all those aspects.
So then it's I'm happy that this facility exists, Marc. No, but then really, indeed, what you see is that your clients, which are fabricators, I think, but also sometimes even project developers.
Yes, well, the main people who are looking at fatigue are the people who own the asset, so own the wind farm, and these are basically the electricity producers and the project developers. They are the main people who look at this type of aspects, basically.
And also so you have also, let's say, yards that produce according to a certain welding procedure. Do they also sometimes propose innovations in terms of, or are those mostly, let's say, the universities that they say, hey, these are new? Who comes, let's say, with a new idea on fatigue improvement or?
Well, most of the time it's companies like you, just like Tree Composites, for instance, or other people in the market to come with a new type of technology, because manufacturers will say, look, we will execute to what we have received. And sometimes they say, look, going to the product developer and they say, okay, right, we can do this better. But the product developer will say, no, just do it like as we said, because they are giving it out to different type of people, and then they will tender that out.
Could you say that it's a conservative industry?
It's definitely a conservative industry, because the stakes are very high. We're talking about a wind farm today is a multi-billion project. So the stakes are high, and the certification bodies and the regulations all around it, is they are conservative. Today, they're moving, they're trying to get it along, but that takes definitely a long time. But nobody wants to take, it's always the developer who takes the final risk.
Sure, but the flip side of that is that if you have a revolutionary development, that the impact of that will be huge immediately.
Yes, definitely. If you have a technology who can improve the fatigue performance, that's great, because the material has got a fatigue performance. That's one thing, but it's always the joint which is the limiting factor.
Yeah.
It's like a chain on your bike, and it's the weakest joint which determines the lifetime of your structure.
And that's where you come in, Marco.
Definitely. So, Mark, I can ask you a pretty biased question as an inventor of red composite joints. So we tested some large full-scale joints in OCAS together with you. How would you, from your words, say how they performed compared to the welded joints that you've been testing for decades?
Well, in welding, we talk about percentages, let's say if we can already improve it by 10 or 20%, it's a great achievement. 20% means about, on a foundation structure, it means about 10% of cost saving. Mm-hmm. And suddenly we tested joints, which exceeded not just by 10 or 20%, but which could present a lifetime increase with more than double digit. I think it was 50 times or something like that, or whatever. So maybe you don't need that 50 times, or even when it's 10 times, but it's much more than we have ever seen so far.
Yeah, thank you for unbiased answer.
but that has an enormous impact, potentially.
Yes, if this is applied, it can definitely have an enormous impact.
Yeah.
It has an impact on the way we maybe look at things, the fabrication side. But if this is being confirmed and being implemented, it can have a big impact on CapEx. Or you say, well, I'm going to play a bit safe. I'm going to use it for my life extension. I was looking at for a business case of a welded improvement of 20%, and it was now a couple of years ago, it were 12 megawatt machines. Now it's more 15 and even higher. But for 80 foundations, so that's just under 1 gigawatt, if you could achieve the full 20% on the critical welds, it would present a saving of over 100 million euros on that. If you could do it under the life extension, with the figures at that time, we come it even bigger a saving per year. So we're talking about...
why is that then? Because you said, okay, lifetime. So instead of, let's say, 25, it becomes 35. Where is the real benefit in this lifetime extension, according to you?
Because then if you depreciated everything and all your investment over 25 years, and suddenly everything is working fine and you can still prolong it by another 10 years, it's a cash cow. It becomes more of a very profitable business then.
So the asset remains, let's say a longer lifetime. It is just a higher value of the asset.
It's a higher value to the asset again.
Could you say that the whole business case is put on its head through this?
It's maybe not put on its head, but it gives a fantastic opportunity to improve the whole business case. So, and the implementation of the whole thing through the whole chain.
Mm.
Really, really nice.
Something to digest.
Exactly, I was thinking about it. So
yeah.
And then maybe one of the things that I was curious to know is, when we first reached out, we of course explained a little bit what we did. Were you in any way skeptical on what we were saying that it would perform, or would you say, well, I'm open-minded on this?
No, I think we were very open-minded. Because we have been dealing with innovation so many times, and we knew that the joint is the critical part, basically. And when you look at when you put all the fibers in all different type of directions, you basically know, yes, this can work. But I was expecting it to be a little bit better, but we were not expecting it to be so much better. So it means, okay, we don't have to have the full the full thickness or whether the full 50 times or whatever the number basically was. But it opens room for improvement. It opens room to do maybe less, to make the wrap maybe cheaper, and still be much better than a classical joint.
Okay.
Now, provided, of course, all this proves right, and it's applicable into practice. It's like in welding, you sometimes have to overhead weld as well above your head.
Yeah.
And the robot which weld downwards is of course much easier. So that has to be all the things that have to be proven. But there is really big option that this can be a game changer.
And not only in offshore wind, I would say.
No, well, today I understood you entered first of all the offshore wind business, but it's about fatigue. So it's all the areas where fatigue is a dominant factor. Think about also all the infrastructure. Mm-hmm. Bridges, for instance. You design a bridge, and in the meantime, you see, traffic has increased so much. Why we're having so much problems? There's not much money to maintain them. Traffic has increased, and plus now all the electric cars get much heavier, which was not calculated in either. So there are always safety factors. That's why these things keep going on. But if you can already, definitely from an infrastructure asset owner, or when it's a government, when you can sell this on a much longer lifetime, it's really a no-brainer, basically. Think also about maybe other areas like aviation, where is also very much in fatigue. Yeah. So I think there are quite a number of options to exploit, which I'm definitely sure you're already doing, Maxim.
Yeah, we're doing a lot at the same time, and we also see that we have to focus, right? So and I also I think one reason why we selected, let's say, offshore structures, let's say in the wider sense, but we see the bigger numbers of jackets. There we really see that the welding, actually also the time that it's needed to do it, and also the NDT, so the testing of whether the weld is properly made is one of the limiting factors, and takes so much time and effort to actually ensure that the weld is reliable. And now I think when you look at what we do with composite joints, there's also an opportunity to speed up that process. I think we discussed it last time as well, is that where a weld is super prone to corrosion, to, let's say, imperfections, minor imperfections, we now have a joint which is not prone to corrosion and also allows for a lot of, let's say, imperfections to be there, because we actually can have let's say, very reliable, stable prediction of how the lifetime actually, what the crack will do. And that really, let's say, it also gives me an additional confidence with you when you really voice out as in, okay, this could be a game changer. And one of the things that we've been discussing also, Marco, over the last few months, is that we actually also see opportunity to strengthen indeed existing infrastructure, and that we are able to even, if I'm correct, Marco.
Definitely. So the technology is proven now that it can work without any welds, but it can also be used to strengthen structure that are existing and have welds, or as a hybrid.
Yeah. So basically, if you have a bridge that needs maintenance on the structure, this might be applicable to that as well.
And we talked about it. It was already existing, but what would we bring in terms of a difference, Marco?
Well, it will be different way of looking at the design of these structures, and also the maintenance strategies for these structures. So if we strictly speak about the scenario where an existing welded structure will be retrofitted by composite, we will not only be improving the mechanical performance, but also resistance to the environment, to the influence of corrosion, because composite being put around steel also prevents the corrosion as the best possible coating that you can ever put on steel. Yeah. We've tested that in our laboratory with different types of scenarios, with fibers, without fibers, with resin, with bare steel, and we've seen that when you put composite with even a small thickness on top of steel, that it really prevents corrosion of steel underneath.
And am I stating correctly that there are, and I don't know if they've ever been tested at OCAS, like strengthening, let's say, type of composite being applied, but they are able to predict actually the performance? That is my question. Is what was out there just a reinforcement and we know that it works, but we don't understand it?
I think we made a really breakthrough in a couple of years ago, and still making that the prediction capabilities with all these tests, and including the tests that we have done at OCAS. We are improving our models to predict these crack initiations, propagations throughout the material on the bond between steel and composite. And in past, it was primarily based on let's put something on steel and hope it works.
And now we know that it works.
Yes, we know, and we know how it works.
Yeah. Yeah. Mark, maybe you're not the right person to ask this question, but the question that I have is there. What does this mean for the companies that manufacture steel constructions? Do we have any idea?
Well, yes. Well, that's the whole part still to prove, of course, because you can make 1, 2, or 3 nodes, but if you make a full jacket, and from that jacket, I was talking about the 1 gigawatt found, which were 80 structures, and you have to make this maybe in a year or 2. Maximum, it's a big challenge. It has to go fast, very quick. So it has to be automated, maybe to some to some degree, and you have to make this capable in volume and under different circumstances. This is the part, of course, which has to be proven still. But then again, it depends on how Tree Composites is going to behave, and is going to be a technology provider, is going to be a manufacturer, or whatever. That all depends still, but I'm definitely sure that manufacturers are looking very closely at this, and I definitely want to interact, maybe to give a couple of tips to look at, because welding will always be there to stay. It's a proven technology, but maybe it can go hand in hand with this technology before the whole technology takes over in certain type of applications.
Yeah.
So the manufacturers are definitely very interested.
Well, I'm also always asking because, at the last couple of months, we were talking about European autonomy with regard to manufacturing structures like that. I would say this is an opportunity for the businesses.
It definitely is, because we see the pressure of going it out. You've got structures being made maybe in Malaysia, in South Korea, in China, in the Middle East. So you've got different markets, and then they're being shipped over to here, and then the consumer maybe between 30-50% of their lifetime already, and we have not had any benefits. So the whole substructure is basically being built elsewhere. We're talking about now about foreign or non-EU or not EU wind turbines even. So I think this is really an opportunity for the European manufacturing industry as well.
And Marco, if we talk about raw materials, this is a benefit as well, wouldn't it?
Definitely, because then we can boost Europe's production of materials here on the ground. And I'd like to come back to that, what you said, that they consume 30 to 50% of their lifetime. Just for our listeners to understand better, we are talking about if you go to a supermarket to buy 10 eggs, you come back home with 5 eggs, because only due to transportation, these structures suffer so much fatigue loading due to waves on these barges and ships while they're transported all around the world, that they actually consume 30 to 50% of their fatigue lifetime when they're welded.
Wow.
And being made all across the world.
Yeah, but it is indeed, so what is the reason that we don't make them locally? And I think it is because indeed, we've been talking about it, that's a challenge of the European manufacturers, is that they have to produce fast with limited amount of space, but also for a cost-effective manner. And welding remains a labor-intensive procedure. So if we don't do anything, indeed, we will have to accept that indeed the structures might be even more heavy due to the lifetime consumption at the other side by transportation, or we do what we do and actually make it lighter and faster to build. That's actually what we're after. And then somebody also asked me, hey, when is this journey actually complete for you, right? When are you happy? And I was thinking about it, and I now know, right? So it doesn't stop with implementing it in offshore wind. I really think that this technology has the potential to really become the new standard of complex welds, where you really suffer, let's say, from the downsides of welding. So if that's where I think, okay, when we reach that point, which will not be, let's say, in the next few years, but that's where I think this technology can go, that it's worldwide applied as solving the fatigue issues with complex welding. But I also, you can criticize this as well, Mark, if you...
No, I think it's maybe also, you've got even if you don't think about fatigue improvement, you've got a second technology which is equivalent, at least, to welding, so we can increase the whole productivity, because now today the whole problem is you can only make so much structures per day or per week.
Yeah.
And if it can help also there,
and
output and rollout of the number of structures we have to make, productivity is a very important point.
And at the moment, that's because welding is relying on manual work, and there are developments of robotic welding. And with your laboratory and your facility, you're also busy with testing those. And maybe there I can offer a bit more unbiased question to you. So if you would try to compare at the moment these robotic welding techniques that are also being developed and what we are developing with composite joints, how close or how far apart they are, and do you see them as a competing or as a complementary technologies for future of Europe?
Well, previously they would have said steel and composites are competitors. In this case, in your specific application, I think it's a hybrid solution. They're very complementary. So it's all about getting the best out of the structure. That's it. The lowest possible cost, weight, the easiest to make, the most productive. That's what you're looking for. And if that is by manual welding in some case, or parts of it, and by other parts of it, you do automatic welding, or you use the whole wrap, the Tree Composites plastic reinforced wrap. That's basically it. So it's not about competition, it's finding the best solution for the substructure. And it might not be just one solution, it might be a combination of those solutions. But I definitely can imagine yours is one of them.
Thank you.
Wow.
Yeah.
That's amazing, isn't it? Because we're talking about something. We often talk about the composite revolution. We like that term, of course. But basically, when I hear you, Mark, when I heard you talking about this, and of course you talking about a background of testing this kind of structures, it basically is a composite revolution, I would say. Or am I overstating now?
It has to be proven. It has to be proven still.
You're talking to
engineers. About the whole certification side and so on.
Yeah.
I'm no doubt they're going to get there, because I've seen things we've done testing together. I've seen things and I said they're going to get there. It will take time.
Yeah.
It will take a bit more time, but they're going to get there. And it might potentially indeed revolutionize the way we look, or the way we make structures. But then definitely more important is how we can design these structures. Because if, for instance, certification bodies would say, okay, all right, you come start, here is your A label, you're certified and so on for use into such offshore structures. You can use higher fatigue classes and design, and here is the proof, the written evidence that indeed that can happen. Designers will need to think differently about this, and the ones who do that in the first instance will be the winners.
Wow, wonderful. Thank you very much, Mark. And Marco, of course. Thank you very, very much for contributing to Future in Steel. There will be many episodes with all kinds of other parties, of course. But of course, you having been testing the joints already and telling about that, we really, really appreciate it. Thank you very much.
You're welcome. Very much.
You've been listening to Future in Steel, a glimpse into Europe's industrial future. With thanks to Marc Vanderschueren and Marko Pavlovic on behalf of Maxim Segeren. If you want to know how your company can benefit from the composite revolution, or if you are interested in investing and becoming part of this development, don't hesitate to contact Tree Composites. They'll be happy to be of assistance. And now, my name is Coach Woltjes, and see you in the next Future in Steel. You have been listening to The Future in Steel, a podcast series about the composite revolution, brought to you by Tree Composites, winner of the 2025 Chamber of Commerce Innovation Award. If you haven't already, please subscribe to this series on your favorite podcast platform, or visit the Tree Composite website for additional resources. Thank you again for listening, and we look forward to bringing you more insight in The Future in Steel.